how it is.
Okay, so we're going to start off with Olexandr Isayev, who's at Carnegie Mellon. He grew up in Ukraine, came to the States, got his PhD at Jackson State. Actually, and then postdoc at Case Western. Spent time at UCLA at the Army Labs, and then several years at University of North Carolina in the Department of Pharmaceutical Sciences, where he really began doing a lot of work in machine learning with applications to developing more accurate force fields, but also in parallel with this, thinking about ways of improving density functional theory and other electronic structure methods. And I believe that's what he's going to talk to us today. So
yes.
Just take it away.
Yeah, thanks, Ken. And thanks for opportunity to present what we've been up to. Let me share my slides. Okay. Okay. Can you see my slides, I guess? Okay. For today's talk, I choose this kind of extremely hypey title of Supercharging Quantum Mechanics with Artificial Intelligence, just to show, a few things and kind of motivate, the audience for, next two talks, who will probably really talk about more chemistry. So before I run out of time, let me acknowledge, members of my lab, and in particular, Roman Zubatuk and Khatice Gökhan, and funding by NSF and ONR, and of course, a group of Adrian Royberg from University of Florida, who is my partner in crime, collaborators from Los Alamos, and a lot of computational resources from various agencies. Now, let me start and show the motivation where our work starts is, when you look for, this kind of cartoon representation of various methods and how they scale versus some kind of metric of accuracy. And basically you can go from, kind of linear scale force field type of methods, climb this ladder by, semi-empirical density functional theory or coupled cluster theory, which actually, you have to pay the price if you really want to do this accurate calculation as the 7th power of number of electrons carried. And, of course, that there's not only an accuracy, but also uncertainty. The force fields can be really accurate, but also, can be really, really wrong. And there is no systematic way how to improve it. And, the rigorous way how to do it, if you want to actually, shrink these error brackets, you have to climb this ladder. When you get, some empirical tight binding methods, you have smaller error, DFT smaller, and somewhere here you have the heaven of full CI complete basis set, which is practically unreachable. So our spoiler alert, and the way why machine learning attracted all this hype and attention is the promise to find methods in this left corner. We can approach the accuracy of the reference theory, right, that use for the training data, but also maintain the pleasant scaling. And therefore, I think what is underappreciated as all of this is due to to development in hardware and software, and historically quantum mechanics been perceived as slow, tedious, one at a time calculation. You take molecule, calculate property of energies. But over the years, for example, Adrian and I, we essentially accumulated quite substantial database of molecules. So currently it's getting around 50 million-ish molecules records for energy properties, geometries, and then using a particular way how to represent molecules for the purpose of learning, we can use machine learning to actually predict some of these things. And and if you're interested in specific mathematics, there is the reference for our paper. And basically why it's possible. So very quickly, this is the time independent Schrödinger equation. which is why we have these large machines to run. However, if you look at it from the point of view of machine learning, this is a regression problem where the ground state energy would depend on this magic function f of molecular coordinates. And so in our work, we use a particular method, family of methods called neural networks, where you feed molecules to neural network and train to predict energy. Since neural networks are fully differentiable, you can backpropagate and calculate gradients and forces, and you can do fully featured molecular simulations. Now, so here is what's been working for past several years is what's called ANI framework, and this, to my example, to my knowledge, is one of the first example of transferable neural network. So if you draw us, if you give us a reasonable organic molecule, will give you energy and forces, typically with an accuracy RMSE about 1 kcal per mole against our reference DFT theory. So very briefly, how it works. The secret sauce has two components. One is a particular way how to represent a molecule, and here it goes back to 2007. Seminal work of Beller and Parinella is to represent molecule as atomic environment. In our work, we use a particular, slightly different functional form of this environment, but the idea is the same. So every atom is represented by the spherical atomic environment, in our case, right there around 5 angstrom, to encode, your nearest neighbor. And therefore, essentially, your neural network would zoom in on one of each environment at a time, and the total, essentially, total energy of the molecule would be sum of this environment. So in practice, how it works, you train your QM, then you pass it to featurization, and each environment, pass through a neural network, then essentially predicts this fictitious local atomic environment. You sum them up to a total quantum mechanical energy. Then you look for the error with reference QM, calculate cost gradients, and update the neural network. This is the training. You iterate many times. So currently, we parameterize 7 elements. So if you give me a molecule with this, neutral molecule with the 7 elements, it'll give you energy and gradients. More elements come in the pipeline. So we extend them from typical, medchem organic chemistry to more interesting elements. We started with a choice of particular DFT functional, this omega B97X, this double zeta. But recently we made the switch to slightly, better modern functional, again from Martin Head Gordon, this hybrid range separated meta GGA and triple zeta basis set. And in addition, we also have a neural network being trained to approximate couple cluster energies with complete basis set superposition. Now, so essentially, what's emerging right now is the new family of force fields. Most of them being used DFT as the reference, and in ANI 1, the first generation, basically our energy was represented. So the short to medium kind of range interaction, all inside the neural network. And on top, you can also add a dispersion because of the cutoff in an atomic environment. So dispersion is not well described on the distance, and one can use the standard Grimet type dispersion to account for that. Now, right now, we extended our capability. Now we can predict, partial atomic charges and various different properties, and therefore you can kind of put more physics and extend, in addition to van der Waals, you can also put explicit long-range electrostatics on, or even higher terms. And also in parallel, we're exploring, another family of methods, which we call AMNet. If time permits, I'll talk a little bit about it, which all interaction passed implicitly inside neural network. So there is no physics whatsoever. Now, again, for we aim first application to drug-like organic molecules, and so the force field can give you energy, accuracy of energies, total and relative energies within 1 or 2 kcal per mole from reference DFT, but also in contrast to a standard force fields, even for these polar molecules that have sulfur, a lot of halogens, we can provide high quality potential energy surface. So for example, here on the right, you see potential energy surface for particular choice of dihedral angles in these molecules, and you see DFT reference and prediction of the neural network. And for most cases, you can hardly see a difference. We can recover even smallest kinks in the potential energy surface. Shape is well preserved. And here I'd like to again emphasize that none of this molecule specifically was used for the training. So this is the external accuracy of the model. And again, the similar accuracy, you can do molecular dynamic simulations, and again, the same accuracy of forces as well. So overall, we have our code on GitHub. It's free, open source in Python, so it implements the neural network and some of the important capabilities for geometry optimization. We have analytic hashing. You can do molecular dynamics. We have thermochemistry, harmonic, quasi-harmonic approximations, and also we're working to implement also continuum electric correction as well. You can work with isolated molecules, use periodic boundary condition for extended phases, and also it works on a GPU. Now, in addition, we're also thinking, can we go beyond just single task or learning energy, and how we add more physics to those methods. So one thought that we have is that if you look for the architecture of ANI, essentially, given the molecular coordinates and the Z number of the elements, we use these atomic environments to kind of give embeddings of those atoms to fit to neural network to produce energy. Now, we were rethinking this architecture to improve on it. So first of all, this embeddings is fixed. It's prescribed by the formula of the atomic environments. So we can make this embeddings learnable. So the neural network would find this optimal descriptor by itself, given the input of atomic environments. And also we can extend this. The problem is the cutoff and long-range interaction by passing those interactions from one atomic environment to another through a special vector, but everything inside the neural network. So essentially, the kind of the analogy would be the passing messages from one environment to another in terms, of this iterations. And the overall architecture, we call it AMNet. So it's inspired by Bader theory of atoms and molecules. And again, then for mathematical formulation is here, paper last year. But here, just to show you a couple of examples, what we can do, for example, we can and also we can train for multiple properties. So for example, we can train for gas phase energies and continuum solvent energy, for example, SMD model. And then what we can do, we can really compare our calculation with the observable quantities. For example, hydration, solvation-free energy. So we go to a database called MNSOL that has the reference values of solvation-free energies. And basically, this is everything computed, again, free energy computed with the AMNet, using the continuum dielectric approximation versus the experiment. So you get the RMSD 1.8 kcal per mole. And this is kind of the accuracy you expect out of a continuum dielectric solvation model. And you see the very nice a correlation between experimental and theoretical predictions. Now, what we do right now is, can we put even more physics? And what we work right now is, can we teach a neural network attach or detach electrons from molecules? So again, if you take the NNet architecture, what we can do, we can condition our neural network on an integral charge of the molecule, and then predict an energy and, for example, spin polarized charge of this particular state. So if charge 0 would be neutral, +1 would be cation, -1 anion, and therefore you predict energies of the corresponding states. And here are some of the results. Again, for a large, very diverse database of organic molecules predicting those cation and anion radicals, first in gas, we could get accuracy to about 3 to 4 kcal per mole. And also what I'd like to point you out, how to read these plots. So this is density plots on the log scale. So essentially most of the points here on the diagonal, and essentially those blue points is a slight outliers out of about 2 million point data set. Now, when you have these quantities, you can also compute corresponding non-equilibrium, vertical, or adiabatic ionization potential and electron affinities to about the same accuracy, 3 to 4 kcal per mole. Now, given that tool, again, this is not perfect, but that can be very useful. So what we work right now, we can now access to a neural network. You can predict energies with respect to a charge. Now, if you can go back, for example, to the conceptual DFT of reactivity, now we can have access to all those partial derivatives with respect to the charges, for example, and we can compute all those nice properties directly by a neural network, fully bypassing conceptual DFT calculation. And therefore, we can calculate all those numerous chemical potential, in the Fukui indices, electrophilicity indices that can be really used to study chemical reactivity. This is what we do right now, and we hope to put preprint quite soon. So one of the way to show the physics.
You have about a minute left.
Okay, yeah, this is my second to last.
Okay.
So basically, what's happening is essentially a neural network serves as the implicit spin and charge equilibration. So when you take this molecule, you either attach or detach electron. So as you pass this iteration inside the neural network, so essentially it moves charges around different atoms and essentially work as a neural charge equilibration scheme. So I'm really hopeful that this kind of technology would really help solve us various problems. And just to show you an example, this is a quick movie of the hot carbon vapor, again, done with neural network. So if you do this high temperature simulation, what you see, you start with hot carbon vapor, and you see the nucleation, formation of carbon flakes. You see the formation of the fullerene. And again, this is done with the same neural network. We just add a little bit carbon-carbon bond breaking data. But it shows us this is really one of the ways how we can find and train more transferable and hopefully more accurate force fields. With that, let me finish and leave you with the links and everything on GitHub. If you're interested to use it, again, our data sets available and the plugins coming to your favorite QM packages. Thank you very much for your attention.
Thank you, Olexandr. So we have time for a few questions. Does anyone on board have any questions?
Yeah, I have a question. Yeah, it's really fascinating. So I saw in the beginning of your first slide, you had that NVIDIA logo, and I was wondering, is there
what logo?
Yeah, the NVIDIA logos. I was wondering whether there are potentially ways to develop hardware that is, optimized or specific to, what you're trying to develop, or whether, just using sort of generic hardware that just needs to be programmed is good enough.
Well, again, neural networks really, flop hungry. So we use GPUs, specifically NVIDIA GPUs, and we use their software stack. But we also can take advantage of this tensor cores that are more specialized. And NVIDIA engineers actually help us to develop, and adapt some of the parts of the code to run with the efficiency. However, I think there is a quite a few startups who do this neural computing, FPGA type of chips for deep learning, and we could take advantage because we use a PyTorch. This is one of the two leading frameworks for neural network, and those chips are typically have the capability to run PyTorch. So in principle, all of the specialized chips for deep learning would run simulations like that.
I see. So you don't necessarily think that there's like something that could be done like at the where there's like redesign, like a lower level redesign of chips could provide further enhancement.
That's probably very expensive. I don't know. But I'm happy to talk, because, who knows? There might be opportunities that I had no idea about.
My son is working in this area. He's working on coarse-grained reconfigurable architectures at Stanford, and he's doing an internship at NVIDIA this summer on using machine learning tools to help with the placement of circuits. And that's just triggering these questions.
Yeah. Oh, wow. Peng, do you have a question?
Yeah, Alexander, first of all, great talk. And I wonder, when you expand the neural network from, carbon, hydrogen, oxygen to include more elements, do you have to include any special treatment, especially for those heavier atoms? Do you have to modify the layers, or do you have to include more, data sets in your training model? I just thought, because their electronic structure is definitely more complex, right? So is there any?
Yes. So the hardest we doing right now is iodine. And this is basically, it uses the core potential. So this is not full electron calculations. You can use pseudo potentials or some other things. But yes, in principle, as soon as you move to, transition metals, and a nice segue to the next speaker, then you'll have to care about the spin states, all the maybe non-relativistic, relativistic effects, and all the things. But at this point, our realm is simple, elements.
Okay, if there are no further questions, let's thank Alexandr again.
Thank you.
Thank you very much. So next, Heather Kulik will be speaking. Heather got her bachelor's degree at Cooper Union and her PhD from MIT with Nicola Mazerai. She then did postdocs at Lawrence Livermore and at Stanford, and then rejoined MIT in 1913 as assistant professor, where she's now associate professor. She's won numerous awards. I'm not going to list them all, but ONR and NSF, the Career Young Investigator Awards, JPhys ChemB, a lectureship, and a year ago, the Frontiers in Chemistry Rising Stars Award. She works in a wide range of areas, including designing new materials, working on catalytic mechanisms, using machine learning, not only to explore chemical space, but to come up with diagnosing problems in density functional theory, cases where problems are really multi-configurational. How can you learn when that's going to happen and your density functional method's going to have trouble? So let me turn it over to Heather.
Thanks for the introduction and for the invitation to speak at PQI today. I saw some of you in the fall and had a chance to speak about some of the work. So I thought I'd do something a little different. And the first half of my talk will be a brief motivation and introduction of some of the work we had talked about then, as well as some stuff we've done since then. And then I will actually be moving back towards some of the organic molecules you just heard about in the second half of the talk. So where we started when I started my research group at MIT about 5-6 years ago is we were interested in bringing high throughput screening to open shell transition metal chemistry. And I should mention that everything I'll refer to here is done in MolSimplify automatic design. But all of that heavily relies on Open Babel tools, which Jeff Hutchinson's on the line today, which are the back end. And a lot of this came from the idea that a lot of the organic chemistry, therapeutic drug discovery, high throughput screening tools worked really well, but just needed a little help from first principles for open shell transition metal chemistry. And once we started developing those tools, we took them in two directions. One was just to bring ideas of high throughput screening into transition metal chemistry and catalysis and functional materials. And so what this meant, and I don't have time to talk about any of this work today, but what this meant is that conventional studies I would have carried out as a grad student on maybe 50 new materials, we were fairly easily able to extend up into the scale of around 500 catalysts, and do it all in an automatic fashion. And what that in turn allowed us to do was to break chemical intuition, break expectations, and identify exceptions to the rule, just by expanding to a larger variation than we normally would. And this meant simple things like violating the Hammond-Leffler postulate, breaking what's called linear scaling relations, and so on. But we were really interested in being able to design materials, and what this allowed us to do was visit small chemical space neighborhoods. It didn't really allow us to do large scale exploration. So starting in about 2016, we realized that we had this tool that let us generate data in a really streamlined way of transition metal chemistry, and we wanted to be able to go out and explore bigger spaces. So what we set about doing, really first starting as a homework problem in the first year of grad school of John Paul Janae, a grad student in my group who's since completed his PhD and is now at AstraZeneca, was to figure out how are we going to tackle unique challenges for machine learning properties of transition metal complexes. And for instance, the conventional approach is to treat all atoms equally, and it certainly was at the time, whereas we know that in inorganic chemistry, there are lots of simple heuristics and rules where really just knowing the direct metal and its coordinating atom tells you most of the story of how a transition metal complex is going to behave. That's how ligand field theory works. So we had these ideas that the right answer was somewhere in the middle. And we wanted to go ahead and start to build models that could allow us to accelerate the exploration of the space of all possible transition metal complexes. And specifically, this was already alluded to, some of the challenges for mid-row transition metal chemistry, I'll only be talking about the first row today, are to think about questions of multiple spin and oxidation states that give rise to distinct electron configurations. And so I always like to say that when we first started out doing this, JP came to me and he said, what would you like me to build a machine learning model on? And for context, briefly, we had MolSimplify, which was using a DFT library of metal ligand bond lengths. And so some of the things that I wanted him to do were I wanted him to use no geometric information. This is very much at odds with what people do when they build a potential, is I wanted him to actually predict the metal ligand bond length because we didn't have access to semi-empirical or force field tools that could give us that accurately. I wanted to predict the ground state spin of these molecules as well as the sensitivity to the underlying exchange correlation functional. And these are actually the first three things I asked him to do as part of his homework as a first-year grad student. And, you know, I like to say that in part, the reason I gave him such a tall list was because I was so confident that I would not be replaced by a machine learning model. I thought my hard-earned decades worth of chemical intuition was going to outpace a model. And obviously I came around, and some of the tools we developed in those early days were readily extended to many other properties. Once we had a formula, they generally worked across a range of different types of energetics and properties. We always work with mononuclear octahedral complexes. Extensions beyond that are something we've done more recently, including the metal organic frameworks with multiple metals. I don't have time to talk about that today. We started with sets of common ligands, metals in multiple oxidation and spin states, at least 2 spin states, at least 2 oxidation states, sometimes more. And we simulated, or we accounted for the effect of sensitivity of the exchange correlation functional by training on a family of functionals, which was something, which was one way that we could attempt to understand how sensitive our ML model was to the underlying training data. We've also since gone beyond that. I'll hopefully put a plug in for one of the ways we've done that more recently. And so one of the key things we focused on early on was thinking about how are we going to choose to represent a transition metal complex to our machine learning model. And if we were in the limit of these very large data sets people often work with in organic chemistry, this would be no problem. But all of our transition metal complexes are at least an order of magnitude larger than small organic molecules. And so to just get a single training point takes us hours or days. So we were working with modest data sets. And so we needed to give the models a head start by giving a good relationship in the feature space that would represent what the model should be learning. And so the very first way we did this, I actually just sat down in a room with JP and I thought about, what do I know about a transition metal complex and what's important? And the reason I still talk about this very ad hoc descriptor set is it actually worked. But we then went back and did it a second time, so I'll show you both of them side by side. So if you think about what matters in a transition metal complex, you have the metal center, coordinating atoms, things like the rigidity around the metal, the bond order, differences in electronegativity. This electronegativity difference descriptor is actually something that shows up frequently in heterogeneous catalysis, and for us was motivated by our observations of its importance in some early studies we'd done on DFT method sensitivity to exchange correlation functional. And then we went into the therapeutic drug discovery literature, looked at things like the truncated Kehr shape index to try to get a very metal-focused view of what's in the coordinating environment. And in retrospect, we called it MCDL25. It's a very sparse descriptor set of continuous and discrete variables. But there are other properties. A lot of people care about thermochemistry. We don't particularly care about it, but those properties scale really strongly with the number of atoms. And so we'd call that a more global feature. And you realize even if you put that on one side, the global feature versus these local features on the other side, there's still a gap. And so when we went back and filled that gap in, we instead extended something from the 80s called Barreau-Brodo autocorrelation functions. We call these revised autocorrelation functions. They're products and differences on the molecular graph. And our extensions included changing the properties as well as changing the mathematical form, but they systematically expand across the length scales of the molecule. And we can divide the properties we use, like nuclear charge or electronegativity, into being more electronic or more steric in nature. And so all of the ad hoc descriptors, as I just described, have a mapping back to racks. And we can also describe how important a feature is in terms of how electronic or geometric it is, as well as how metal focused it is or metal non-local. So we can actually use something called feature selection to identify the most important features. And so principal component analysis in a whole molecule feature set versus a local feature set reveals why it's worth it to do this. So on the left-hand side, you have a whole molecule feature set, and you see two transition metal complexes, very different in size, but very similar properties of the spin splitting that we want to predict. Whereas in our local representation, those 2 points sit very close to each other. And so the model has to do a lot less work to figure out that those two molecules behave the same way. And so the result is that these early, even ad hoc descriptor sets used to train a neural net could correctly predict, with respect to DFT training data, 97% of ground state spins. This is something that semi-empirical theories beforehand couldn't do, and so on. And on the same data set size, we were able to reduce, with respect to a whole molecule representation, our errors by an order of magnitude. So if you look at MCDL25 versus these more systematic rack sets, you can see that the systematic approach outperformed my chemical intuition quite a bit. So we needed more than my chemical intuition. We got from about 2.5 kilocal per mole average error on spin splitting down to sub kilocal per mole average error. And the racks themselves are a large set, but applying feature selection gets the dimensionality of the set, which I'm showing here with FS rack or URAC, down to the same sparsity as MCDL25. And you could extend this very easily to other properties such as the solvated adiabatic redox potential, as well as gas phase ionization potential. And the errors were pretty comparable. We could also do things like replace force fields that couldn't accurately predict metal ligand bond lengths with our neural net bond length predictions. We could predict the metal ligand bond length to around a 0.01 angstrom average error, which means that we can actually do some neat things with starting geometry optimizations at the end. But what you might be wondering about is what we could actually do. What could the rack set do that MCDL25 wasn't doing, or why do we get this better performance with this more systematic set? And if we look at MCDL25 in terms of proximal, middle, and distal features, what we see is that I basically juiced things one way. As I said, proximal, metal, local features matter most, and distal features matter almost none at all. Because of the mathematical expressions in the full RAC 155 set, we start out with a lot of metal non-local features just because of how the expansion works. And when we apply feature selection, we end up with a pie chart that looks in URAC 26 pretty similar to MCDL 25. They both agree on distal features, metal non-local features, not mattering much for these properties of transition metal complexes. Where they differ is actually in our lack of creativity in our ad hoc set. So URAC 26 pulls out much more mid-range features, things that involve atoms 2 bonds away from the metal, which were properties that we wanted to describe, but just basically ran out of ideas thinking about how do we describe those. There's more balance between those features and the proximal features in the URAC set, which allows it to be to get lower errors. But test set errors are not particularly interesting in themselves, especially many of you know the DFT functionals we're training on aren't particularly accurate. What we found to be the most useful thing that could come out of this work was to think about how do we extract design principles from this. And so I mentioned we could apply feature selection to identify the most important racks. And so I'll color this porphyrin now by which atoms matter most for predicting different properties. I'll color them more electronic if Z or chi matter more, and more geometric yellow if ST or I matter more. And we'll make an atom big if it's important and small if it's unimportant. And so for 2 different spin splitting sets using a different cutoff for how many features include, what we conclude from these is just that ligand field theory works. So the metal is really important, and its nearest neighbors are really important, and their electronic properties are really important. That's what ligand field theory tells us. But it gets interesting if we contrast this with other properties. So specifically, if we look at predicting the metal ligand bond length, which I mentioned we could train a model to do this really well, it's a much more balanced property. So both electronic and geometric properties of the substituents atoms matter, and it's much more all over. So all of the atoms contribute. You can imagine the atoms directly in the bond are important, whereas steric effects a little bit further away can have an effect on how long that bond length is. And then where things get really interesting is that redox potential lights up an entirely different part of the molecule. And so we can now have a roadmap that tells us that if we want to, we can change the spin state of a molecule without changing its redox potential, or vice versa, if we focus on our tuning on different parts of the molecule. And a specific example of how that maps back to real molecules is provided in our 2019 inorganic chemistry paper. In the interest of time, I don't have time to go through that today. So that was a nice story of what we did early on to start to machine learn transition metal chemistry. But if we want to go ahead and use this for chemical discovery, we encounter several roadblocks, which is what I'd like to spend the rest of my time today talking to you about. So specifically, we have uncertainty that I have touched upon and I will come back to a couple times. And one is the method choice. So from our perspective in accelerating chemical discovery, what we care about most is if we change the level of theory and what goes from an excellent molecule that can solve an outstanding materials problem instead becomes a hopeless molecule that is worthless. And so if we could get to full CI and know what the exact quantum mechanical answer is for what's a good molecule and what's a bad molecule, then that would be great. But in practice, we really can't. So one thing that's important is to know, when do these molecules become leads versus stop being leads, depending on the functional. And we can address this somewhat with knowing the sensitivity, which is something that automatically comes out of our machine learning model. I'll show you some additional work beyond that in the second half of my talk. Another thing that I'll also come back to is that not all of these calculations succeed. If you either have a new grad student in your lab learning inorganic chemistry with maybe limited background in the practical and heuristics, they can easily set up calculations, geometry optimizations that will fail. The molecule may not be stable. The molecule may not be a reasonable one. It may not be reasonable to carry out DFT on. So it's not uncommon, either if a calculation is spawned by a suggestion from a machine learning model or by a human, for more than half of these calculations to fail and significantly waste computational time. So that's another challenge for letting a machine learning model pick for us how to study new molecules. And then a third issue is the uncertainty in the machine learning model itself. Ideally, we'd like the model to be able to tell us when it knows the answer and when it doesn't. And so people have spent a lot of time working on this. Two common approaches people use are either to train an ensemble of models and then hope when that ensemble differs, when the variance is high, then that is a good indication of error. We have actually found some superior performance from either in heavily feature engineered sets using the feature space distance, or more recently, we developed a metric of the latent space distance. In both cases, what you think about is how far a new molecule is from anything the neural net has ever seen before. And this can be good when the variance of an ensemble of models insufficiently disagrees. So say all models are wrong, but they're wrong by the same amount, the variance can be overconfident. And that's a technical detail. All of these are covered in some of these past papers, but it factors into how we thought about using machine learning models for chemical discovery, which I'll talk about now. So once we have a neural net, especially if you're not used to running DFT calculations, it's important to remind you that we showed we could get the DFT answer, which we're going to treat as the ground truth for a moment, within a couple of kilocals per mole if a molecule represented something very close to the training set, even to sub-kilocal per mole accuracy. So we can easily score a whole landscape of millions of molecules, thousands of molecules, any number of molecules with one of these models. But one thing we should think about doing is, of this candidate pool of thousands and millions of molecules, is where does the model actually know what it's talking about? And that field in general is called uncertainty quantification, and it's a challenging one where advances are still being made, but we would want to exploit the model by knowing where it's certain and then pairing that with an optimization algorithm to find only the leads that the model is certain about. And so the first time we did this, we actually did this with a high school student, Lydia Chan, who's now at Stanford, and we implemented a genetic algorithm. Genetic algorithms themselves are nothing special. You just encode a transition male complex as a gene. You evaluate a fitness function, so your target property. And the thing that is a little different about what we're doing is we're using the neural net to score how close we are to the target property. The fittest survive, we have mutation and crossover until we end up with a local population of the best results. Now, what we specifically did that was a little different is we introduced the uncertainty quantification for the model to exploit the model in the way that we go back and we think about either feature space distances or latent space distances. And in particular, if we just let the model make a prediction anywhere it can, the errors can rise dramatically. But even simple models of UQ, the first time we did it with just feature space distances, if we set a budget, a tolerance for how uncertain we were willing to be based on how different a new point is from all existing prior data, either in the feature space or in the latent space, which is the last layer of the neural network, we can drive down the errors. And so the way we're going to incorporate this into a genetic algorithm is to just combine a composite fitness function that penalizes being far from the data, either in the feature space distance or the latent space distance. And so when we did this, it worked. So what I'm showing you on this slide is almost a near copy of what I showed you on my first slide, but now we're looking on the scale of thousands to tens of thousands of new catalysts and materials where we could control error. So we could ask the neural net, find me something with a 4 EV band gap. And when we verified it with DFT, we got a band gap very close to the average of what the neural net was seeking out. But we wanted to go beyond that. So this is just exploiting models. What you really want to do is address bigger problems in a way where we don't train a machine learning model beforehand in order to be able to answer a problem we have. And so we really wanted to do this on catalysis, but I convinced myself that redox flow battery, redox couple design was simpler. And so we started there. I've since been told it's not actually simpler, but some of the challenges associated with designing redox couples for redox flow batteries are you want good concentration of the redox couple, you want high redox potential, and you want to avoid crossover. So you need to design really bulky transition mel complexes. A lot of the best redox couples for redox flow batteries are transition mel complexes. And so this is a multi-objective design problem. And this is really where I think machine learning can be advantageous in accelerating design, is you want to think about solving multiple problems that would be really challenging to solve with either chemical intuition or with brute force high throughput screening. And so we addressed the challenge of crossover by designing much bulkier transition mel complexes than we had ever studied in my group before. We started with experimentally motivated heterocycles, merged them together to create core ligands and functionalize them in a way that we could anticipate would address the issues of stability, concentration, and redox potential, mix them with 4 metals. And the result is we had a space now of 3 million complexes. So I started my talk saying we did high throughput screening in DFT to address 500 complexes. At this point, we moved on to a space of around 3 million complexes. And the uncertainty quantification and optimization algorithm approach we were going to use is now a model exploration approach, something called active learning. So we're going to put on our axes the other 2 objectives, maximizing the solubility in a polar solvent, as well as maximizing redox potential. This can be imagined as a trade-off because adding more functional polar groups will improve solubility, but will lower the redox potential for the reasons I showed you on that porphyrin just a few slides ago. And so we'll put log P as our solubility metric and redox potential on the other axis. And we're going to start with as much DFT data as we can get. I'll show you this with real data on the next slide. This is just a cartoon here. And with a handful of DFT calculations, we can ask the neural net, what do you think of all 3 million of these complexes? And specifically, we're looking to push the boundary to the bottom right corner of this graph. And we want to find new complexes that are past what's called the Pareto front, which is the trade-off of all of the best soluble and high redox complexes. And so we can ask the neural net to recommend some leads, and we're going to specifically incorporate the uncertainty of the model in an approach called 2D expected improvement, come up with some candidates, rerun the DFT. Now the neural net isn't going to be perfectly right about all of these, and then retrain the model and iterate through this process until we push the discrete Pareto front of all optimized complexes out further. So this is a cartoon. Let's take a look at what this actually looks like. Because these are molecules that have around 100 to 200 atoms and we're carrying out full DFT geometry optimizations, in about 2 weeks, we get this around 100 points. And this is running on 64 GPUs on our cluster. This is already with maxing out the parallelization that we can max out. And then we go over the neural net, and in about 3 minutes, this is what it tells us it thinks based on that information of 3 million complexes. And we can overlay the Pareto front, and we can look at which ones have the greatest promise. Those are lit up in yellow for going past that front. And so we'll select some of those points and we go back to DFT. We spend another week there, and this is what we get. You can see the model was not that right about that many of those points. Early on, it didn't have that much information. So the Pareto front only moves forward a little bit, but we feed that information back to the neural net. Go again, we pick some new leads. You can see the front is getting less and less optimistic. But the model's getting better. So this time when we spent a week with DFT, we pushed the front further by quite a bit. We go back to the neural net for another few minutes, and so on until the Pareto front basically stops growing. We spent 6 weeks on the DFT. We spent about 15 minutes with the neural net. And the neural net is increasingly pessimistic that we're really going to go beyond this front. And so you can see in the Pareto front we end up with things with both better redox potential and better solubility. All of the points in the Pareto front are from the last generations of the model. And you can ask yourself, well, how much better is this than if we just randomly search this space? And the distribution of properties in the space is not normal. So what I'm going to tell you is an underestimate. It's assuming that we have normal distributions and so on. And what we can come up with I guess before we come up with that, I will say that everything that we find on the Pareto front has fairly convergent design rules. So in addition to how fast is this and how much are we accelerating and improving properties, almost all of these are manganese high spin complexes with sulfur heteroatoms in the ring structure and so on. And so a lot of the design principles are fairly convergent in the space. But we can also ask, could we have figured this out with random search? And what we conclude is we get about 500-fold acceleration. And so when I first heard 500-fold acceleration, I don't know about you, but I wasn't very impressed. But what you have to do is you have to realize is that this was 5 to 6 weeks of parallel DFT computation, and it's 500-fold acceleration with respect to that. And so this is a difference between having an answer in a month versus not having an answer until 50 years from now. And so where I see this going is really addressing bigger problems, higher dimensionality problems that are just really hard to solve any other way. Think about problems where the greatest minds, the greatest synthetic minds, the greatest computational chemists have really put forward their effort in trying to find a new material and haven't been able to find it yet. And with model improvements, as well as further algorithmic improvements, these types of accelerations can even be further improved upon. And this is really, I think, where machine learning starts to overcome kind of the hype associated with it and actually start to do something useful. But I now have, I think, about 10 minutes left to tell you about the second half of my talk, or maybe second third. So I think that's okay. And that's thinking about how we can instead think about what it is we're doing when we are using our expert knowledge to carry out computational chemistry. And in particular, my motivation for getting into this field and into this area of thinking about autonomous computational chemistry is that I realized how hard it was for me as a PI to teach what it took me so long to learn. Like, why is a calculation good? Why is a calculation bad? That is a really hard and tedious thing to teach new students. And it slows them down from learning more important things like what makes an interesting molecule, or how do I program this, or other things that are more rewarding than why did my calculation crash. So if you think about when you're getting into a new area of materials, you have to choose what you're going to study, you're going to consult experts, you're going to choose the method you're going to use, you're going to run your calculations, you'll spend a lot of time checking on them, analyzing the result, deciding if it makes sense. And so we already had a lot of these tools in our autonomous, in our toolkit to start to build towards an autonomous workflow. So we already had tools for automated selection and building of molecules. We already had data-driven models, automated data analysis. And so I'll tell you 2 brief stories about how we started to work towards automated prediction and checking of the calculation itself, as well as knowing when the method is suitable to be used. So this is work that came out last year in 2019. And in order to emulate this effective, I mentioned about half of our calculations can fail. We started with about 3,000 good and bad geometry optimizations, and we had to choose what good and bad meant. And specifically, bad geometry means the molecule forms a structure we don't expect it to form. It has a lot of deviation in its ligands and so on. And the other one was there's a lot of spin contamination. If there's high broken symmetry, we can anticipate that a cone sham DFT result's not going to be suitable. And it turned out we could, if we had this training data without running the calculation beforehand, we could train a neural network classifier on RACs, the same representation we use to predict properties, to instead predict this classification task. Will the geometry optimization fail? Will the system be spin contaminated? But we could only do it to around 90% accuracy. And this is just showing you that you could combine these 2 models and then figure out, well, will you accidentally not run a calculation, or will you run a calculation that would have failed? And the result is that the false positives and negatives are fairly balanced. And you can run about half of the calculations you would normally run in 1/3 of the time to cover most of the feasible space. And that's because the bad calculations take longer to fail than the good calculations take to succeed. And you're also not wasting time exploring molecules that have no promise. But the transferability is limited, so we trained on metal oxidation state 2 and 3 complexes, but we wanted to test it on metal 4 oxos relevant for catalysis, and the accuracy drops dramatically. So if all we've learned is the mapping between chemical structure and those particular successes and failures, a metal 4 oxo calculation fails for a different reason than the +2 or +3, but we could recover some of this by incorporating a UQ metric and only making predictions on the cases the model was most confident on with something we called the latent space entropy, and we could actually recover close to the test set accuracy. But what we actually ended up moving to was thinking more about more transferable representations for the task at hand. So if you don't know yet in a new space if a calculation will succeed or fail, you might still be willing to set up that calculation. And so this is a phrase my postdoc Peng Liu coined, in situ calculation monitoring and prediction. Peng helped out a lot with this work and will be a new faculty member starting at Emory in the fall. And in particular, we could think about in a transition metal complex, different properties we're going to generate as we start that geometry optimization. So we can think about the metal ligand bond order, the Mulliken charges of the atoms, the gradient. This is the electronic gradient, so the gradient of nuclear motion at the metal, as well as the geometry metrics I mentioned. And here what we did, because it was simpler for our data set sizes, we trained convolutional neural networks on these 34 descriptor sets. And we used the time series data to develop models using up to the first 40 steps of a geometry optimization, which is around 12 hours of calculation time, but no more than half of the full optimization. So we're not giving the model the answer, we're giving the model the initial information that happens in a geometry optimization. Here are the specific details of those metrics. And what we see is that this model we call the dynamic model beats the static model, especially in diverse cases. It beats it in the cases the static model was struggling to learn. And in the interest of time, I won't go into it, but we went back and analyzed the model, and what you can learn is that some geometry optimizations fail very slowly and in complex path-dependent ways. And so in those cases, it's just really challenging to know based on chemical composition alone that a calculation is going to fail. Similarly with ones that succeed, but using this information of the calculation as it goes can help make models more predictive. Now, the next step is to think about how to use that information to on the fly change the optimization procedure so that we can turn failures into success or diagnose them further. And that's something we're thinking about now. But I'd like to finish with just our very latest paper, just ASAP at JCTC, I think yesterday or today. And I only have a few minutes, but hopefully I'll do it justice. And if not, you can see the paper online. And we went back to a simpler problem. We went back to the question of, well, how do we know when DFT is the right method to use? Or how do we know when a single reference method will fail and we have strong correlation? And you know, the way people normally do this is they think about multi-reference diagnostics. And so we wanted to cast a really wide net and look at every diagnostic anyone had ever recommended before. People have recommended DFT-based diagnostics based on atomization energy or based on finite temperature DFT, based on the natural orbital occupations of MP2, the leading weight of the CAS wave function and natural orbital occupations of the CAS, HOMO and LUMO. Couple cluster diagnostics are really well known. T1 obviously has some issues, but the closely related D1 that tells you something about the maximum amplitudes of the singles or the doubles, as well as the sensitivity of the atomization energy to the perturbative triples term. Those are all widely used diagnostics, and everyone has their own recommendation for how these should be used. You can also think about these in terms of what they're probing. Are they probing occupations and sensitivity of occupations to whether or not the fixed occupations are a good fit, if they focus on atomization energy or excitations. And here are some recommendations that have been made for about 11 of the diagnostics. You can see everyone has a heuristic and a rule for what diagnostic would be best. And actually here what we use is we use the organic molecules from the NE1 dataset, which Oles just introduced earlier in both equilibrium and stretched stretched molecules. We have things with phosphorus and sulfur and so on in a preprint that is probably also on ChemArchive today. And so what we can conclude from all of this is something that has already been stated in the literature a few times before, which is that if we use these diagnostics on that type of data set, the diagnostics are going to disagree how we cut off and use a cutoff to classify, is this a multi-reference molecule or a single reference molecule? They're also not going to regress well together. They're poorly linearly correlated. And if we try to come up with a ranking and say which of these diagnostics is the best one to use so we can put it in our automated workflow, we're going to judge it against how well we recover the correlation energy. And the conclusion is that correlated wave function theory diagnostics outperform DFT diagnostics. But the problem with that conclusion is that those are more expensive than the DFT-based diagnostics. And so is there any rhyme or reason to this? Do the diagnostics agree on some higher level than the linear correlations? And we can use something called UMAP. It's a nonlinear dimensionality reduction technique. And what we conclude is that the diagnostics actually do agree. On the most extreme points, the blue parts are all the same blue, regardless of diagnostic that we use, and the red parts are the same red. So the most extreme points, there's consensus among all the diagnostics. They say single reference molecules are always in the same spot, multi-reference always in the same spot, and this extends over all 15 diagnostics we studied. And so we exploited this to train machine learning models on the DFT diagnostics that weren't that good, combine that with a modification to RACs, and the result is that we could actually predict the correlated wave function theory diagnostics and recover the good agreement, the good ability to predict multi-reference character from a wave function theory diagnostic at DFT cost. And so it was a lot of technical stuff that I just zoomed past, but we can obtain the expensive but accurate prediction of multi-reference character while maintaining a cost that's amenable for high throughput screening at the DFT level. And we go beyond that a little bit with thinking about how we use all of these together in our most recent preprint online. So I'd just like to conclude, I'm only a minute or two over. We started by talking about high throughput screening and transition chemistry, which motivated for my group new software, new representations, new approaches, optimization algorithms, and so on. And the same types of techniques we first used to accelerate chemical discovery, we're now working towards adapting to try to replace the tedious aspects of computational chemistry, not to replace computational chemists, but to think about how can we make ourselves freer to actually ask difficult chemical questions instead of monitoring our jobs and so on. And so some of the software you can get to from molsimplify.mit.edu, as well as multi-ref-predict, which drove the last bit of work, was developed by Peng Liu as part of a MOLSI fellowship. And so I wanted to call that out in particular. So I'd just like to finish by acknowledging the students who did the work, especially Chenru Duan, John-Paul Genet, Peng Liu, some of the funding sources, and I definitely went over, but just to say, we've done some work in thinking about how do we go beyond just DFT and thinking about predicting experimental properties. That's in this work on the right here, as well as thinking about how do we make smaller molecules so we can generate bigger data sets as well as benchmark our methods better. That's in this paper here. So if you haven't seen either of these, just wanted to put in a plug for those. And if there's time for questions, I'd be happy to take them now. So thank you.
Thank you, Heather. Excellent. So there's time for a few questions. So let's see, Jeremy?
I was applauding.
Oh, you were applauding. Okay. So you wanted to be heard.
More applause.
Olexandr?
Yes, so great work as usually. So back to your prediction of geometry optimization.
Mm-hmm.
A quick question. So different people generate different starting geometries. So there is always a bias how do you generate starting geometries.
Mm-hmm.
So is there a way to include that, or you always standardize and start your geometries by some kind of templates?
So molsimplify, the first thing it ever did was make systematic how the geometry was started. And so the static classifier bakes that in, right? So what it does is the metal ligand bond length is the neural net predicted metal ligand bond length, and everything else is force field optimized with UFF or MMFF to reduce sterics. So we start with really good structures. But the in situ model would not depend on that nearly as much. If we gave a really bad starting geometry, there is a limit where the same thing I mentioned about geometry checks, if you gave a geometry check, if you gave an initial geometry that failed the geometry check in the first place, the calculation in our automated workflows just wouldn't even start. But if it's just a little different from what we've trained on, these types of models only use electronic structure information. And so, for instance, a stretched bond or more displaced bond would inherently benefit from that information. The descriptors would be different. Where we would be blind to differences in the initial configuration would be the static classifier, the first one I showed.
Yeah, there's an interesting food for thought. Since we run millions of those calculations in a simpler system, when you squish them, you can have all sorts of errors. So it's really interesting to see.
Whoops.
Yeah. So I will say I didn't have room for it in this talk, but we have a data set of, we have every calculation our group ever runs is in a centralized database. And we have another paper coming out sort of asking, if you look back at every calculation we ever ran, where was it a bad idea for us to run DFT? Where did things go wrong? What could we have learned? We're now making heavy use of that data to answer questions at least adjacent to what you mentioned.
Yeah, Peng, do you have a question?
Yeah, no, again, so really nice work, and I'm especially interested in the materials design for the redox flow battery. So you mentioned that you use active learning to predict the structures in the next round. I'm just wondering if you can elaborate a little bit about like what the exact techniques and how do you choose like which part to modify based on the active learning techniques.
So I will say when we do this, the pool itself is fixed. So the answer has to be chosen from one of these 3 million results. So we're just trying to answer what is the best choice of these 3 million results. And what we did in this work, and we've since extended it to tetradentates, is we looked at whenever an experimentalist synthesizes a molecule, what types of ring structures have they been able to synthesize? And so we bias the answer somewhat in that things that have been readily synthesized or are within the realm of synthesizability, that's how we address that, are in this candidate pool. And the other thing to note is that we opted and are now testing this on the set I alluded to earlier. This is a smoothly varying set. So there's not like islands of a totally different macrocycle sitting off that has no connection. So when the algorithm can optimize, it can optimize in a space and find smoothly varying choices in a discrete space. The specific algorithm itself is called 2D expected improvement, and all it's doing is identifying where the neural net predicts this new complex is going to be beyond the front, as well as how uncertain the model is, and then we feed that back to DFT. So the answer for our results has to be in the space, but this is an extremely wide space in the first place. We're doing this again now with catalysis, and in that case we have tetradentates. So the rules for building up the tetradentates are even more varied. We end up with 3 million complexes before we even add functional groups, and we're currently just spanning the space without the functional groups, and then we're going to basically implement a more tree-based approach where if a macrocycle is just beyond bad for any given reason, we're not going to then pursue optimization in the functionalized space. So that'll allow us to get up to more like effectively a few 100 million complexes. But we're not doing continuous optimization just in the model because we're doing this approach. The specific thing we're doing is we're feeding leads to DFT, and then we need a discrete molecule. We run the DFT optimization, then we feed that back into the model. Did that answer your question?
Yeah, sounds great. Thank you.
Carl?
It's brilliant work, Heather. Again, it's fantastic. And I was also had this question about, like Peng did on this flow battery. What I was interested in, and I think you kind of answered this already, but basically the answer had to live in this 3 million complexes that you identified. I guess my question is, the human intervention part comes in picking the heterocycles, the core ligands, the functional groups. But I suppose those are like all possible ones that you had, and then the metals. I guess really my question is, what would have happened if you had chosen a different starting set? Say instead of these 4 core metals, you chose different metals instead. What would the model have come up with then?
Yeah, there are a lot of challenges around this. I think one is that the optimization algorithm, answering the second part of your question first, the optimization algorithm is really sensitive to the initial conditions. What does the first model know? And so I think we ended up with some manganese bias, even in the pool we were optimizing in. And so you'd really want to run this 10 times and see what each path gets. But we were not going to run it for 6 weeks, 10 times with parallelization. So that's one aspect. But another, we made conscious choices. For instance, we kept all neutral complexes because to learn the redox potential of a neutral molecule and a charged molecule at the same time, we knew was going to stress a machine learning model. As well as some of the challenges for DFT with calculating highly charged molecules in implicit solvent, which is what we're doing. So the answer is we could only find an answer in the space. The space is just much, much larger than spaces people typically come up with. And as a result, I would actually say that we spent about a year making some of these choices behind the candidate pool. Some of these heterocycles come from the spin crossover literature or these other things. And now what we're trying to look at or answer maybe, because my answer I think is probably not very satisfactory. The answer is if we put vanadium in with different ligands, then we would have found the best vanadium with different ligands, is we're trying to look at everything that's ever been synthesized in the Cambridge Structural Database and trying to answer the question of how do we faithfully understand what everyone's been able to make before, but stretch a little beyond it. Because we've seen in spaces where people just enumerate anything they feel like on, like hypothetically, like we basically did, versus looking at how that overlaps with what people have actually made when the initial choices of your possible answers differ between like what can be made versus what you're going to enumerate, then the model does learn that difference. We have looked at that specifically in metal organic frameworks more clearly and seen that you can reach different conclusions. But I didn't have a chance to talk about that work. That's a preprint from us too.
Okay, so Ryan, is your question a quick one?
Yeah, so for, I guess, back to your candidate pool, do you have any sort of justification for these 4 metals in particular?
So I think the justification is they're earth abundant. We wanted to see, can you find designs outside of vanadium, because vanadium's well studied. And the other thing that was interesting about them is that they can access multiple spin states. And so we were designing the spin state as well as the redox potential at the same time. So it was a space we knew would be challenging to study by conventional means. We did use prior data in the group on redox models that had these metals, but I actually think, and we mentioned this briefly in the paper, that using prior data when the molecules themselves were much smaller was not particularly helpful. And probably to do it again, we might have expanded, but a general focus now for us is trying to design earth abundant materials. So any case where you know a slightly less abundant metal or slightly nastier to work with metal can be replaced with something like iron, we would definitely pursue it from that perspective.
That's smart, yeah. Thanks.
Okay, well, let's thank Heather again. And let's see, next we'll move on to Peng Liu. Peng did his undergraduate work at Peking University, moved to Canada, and then transitioned to UCLA, where he did both his PhD and a postdoc with Ken Hoke. And we're very fortunate that he joined us here at Pitt. He's been very successful in awards. I mean, he's received the NIH Early Stage Award, the NSF Career Award, and at Pitt, just this current year, he received the Chancellor's Distinguished Research Award. Peng is doing a lot of work in complex reaction mechanisms, identifying transition states, reaction pathways. And so it really ties in, I think, to both of the talks that we've heard so far. So,
Yeah, thank you, Ken. Following the wonderful talks from Heather and Alexandra, I almost want to talk about a machine learning project, but unfortunately, I had to switch the topic a little bit back to DFT and also using energy decomposition analysis, but use these to guide the practical catalyst design that facilitate experimental discovery. And my group has worked in several different areas, but always very closely with experimental chemists in terms of using homogeneous transition metal catalysis to facilitate new transformations in terms of synthesizing small organic molecules and also polymers and even carbohydrate molecules. So the apparent reason these catalysts are promising for these synthesis is because several reasons. They comparing to traditional synthetic routes, they often offer more straightforward pathways which were not available to uncatalyzed conditions, and basically can dramatically reduce the number of steps. And they also offer abilities to catalyze transformations using unactivated starting materials such as inert carbon-hydrogen bond or unactivated carbon-carbon double bond. And probably the most importantly, many of the transformations are regio and stereoselective, which is very important in synthesized functionalized molecules such as drug candidates. And then in terms of developing those catalysts and new catalytic transformations, almost in every single case, we always want to ask the questions whether or not we can understand mechanism or even design new reaction pathways through those mechanistic understandings. And also, how do we improve the catalyst reactivity and the selectivity by altering the catalyst structure? So, and of course, by doing so, computational chemistry has contributed a lot in terms of studying those transition metal catalyzed reactions. The apparent reason is actually fairly straightforward to use DFT to calculate the so-called reaction energy profile. We can calculate the structures and energies of intermediate and transition states. And once these are obtained, at a reasonable level of theory, we can use this to predict which reaction pathway is more favorable, and we can predict how ligand and substrate would affect the rate and the selectivity. So the bottom line is we are getting really good at using computations to explain things, right? And then the next big question, of course, is how do we transform from explanation to prediction? Whether or not we can use calculations to guide the catalyst design or the reaction discovery. Unfortunately, I'll have to say, in the field of homogeneous transition metal catalysis, the current way that new reactions are discovered still hasn't really changed since decades. So basically, usually there would be starting from some sort of like a chemical intuition, usually guided by literature precedents of similar transformations. And based on that, basically a small library of catalysts would be selected, and then they will be tested experimentally, and that will basically is the way to catalyst discovery. As a computational chemist, is set to see this, right? Because as you can see, computation is not really part of the whole catalyst discovery or optimization process. So what we envision is maybe we can propose a way that we can change the traditional way that people develop a catalyst experimentally. But of course, there is still going to be relying on a fairly close interaction and collaboration with the experimental chemist. But the idea is we can introduce computation results at a relatively early stage, followed by some simple mechanistic studies then we can identify the rate and the selectivity determining steps. Then we can use calculations to really guide what substrate or ligand we want to test experimentally. And those experiments can in turn validate the computation, and maybe we can do this after a few iterations. We can sort of optimize the desired reaction, the catalyst structure. And of course, a big question for this is how do we really use computations to make suggestion to experiment, right? So how, because as Heather mentioned, even for very simple catalyst structures, you might have like millions or maybe even more possible structures that you want to consider, and how do we really make good justifications about what type of structures we want to explore, both computationally and experimentally. So our idea is slightly different from high throughput screening or large scale screening. So our idea is basically based on some simple understanding, or you can say, these are reinforcements of chemical intuition, but then these are based on quantum mechanical calculation of a transition state structures. And once we get these structures, our idea is maybe we can take a really good analysis of the transition state, and then we can analyze, what are the factors that will affect the transition state energy. So some of the known structures, some of the known effects include, sterics and electronics. But then the question is, how do we discover other relatively unrecognized interactions that affect how the transition state energies are affected by the catalyst? And then we can use those insights to guide the experimental catalyst selection. So our rough idea in terms of understanding the factors, comes down to this very simple cartoon. So in a very general sense, for any given transition state between a transition metal catalyst and the substrate, and you would expect that the stability is controlled by several different types of interactions between the catalyst and substrate. And of course, these include the bonding interactions between the metal center and the substrate. And we know the strength of the bonding interactions is usually affected by the electronic effects of the ligand. And on the other hand, there is a number of different types of non-covalent interactions between the ligand itself and the substrate. And the more obvious one is steric repulsion that always people try to understand and think about. But on the other hand, there are other less obvious non-covalent interactions, including electrostatics and potentially London dispersion interactions. We may also contribute to the stability, but the impact of these are just conceptually much more difficult to understand, and that's why usually these factors are usually not incorporated into a chemical intuition-driven catalyst design. And our idea is, can we use computational model to quantify how each of those different types of interactions would contribute to the transition state energy, and then we could use those insights to really facilitate the catalyst selection. So to do this, we proposed this so-called ligand-substrate interaction model. So the idea is, as I mentioned before, it's relatively easy to calculate the overall activation energy, but then we want to separate the activation energy into a few different chemically meaningful terms. So the key to this approach is to calculate the so-called through-space interaction. So the way we do this is we sort of optimize the transition state structure into 3 different fragments, including the ligand, the metal center, and the substrate. And then we build a hypothetical complex in the absence of the metal center, and then we can calculate the non-bonding interaction between the ligand and the transition state at the transition state geometry. And that interaction, we define this as a through-space interaction. And then the rest of the interaction energy between the whole ligand-supporting metal catalyst and the substrate would be the through-bond interaction. And the last term that contributes to the activation energy will be the distortion. And the benefit of doing this is after we separate the through bond and through space interaction, we can use the energy decomposition approach. In this case, we use the Martinez-Gordon's ALMO EDA to separate the non-bonding interactions between the ligand and the substrate into several different chemically meaningful terms, including polar repulsion, electrostatics, intra-fragment polarization, charge transfer, and dispersion interactions. We first tested the application of this model through a collaboration with Buchwald at MIT. So his group has been experimentally developing copper hydride catalyst for alkene hydroamination reactions. So in this particular example, I showed the DFT results where we demonstrated if you use this DTBM SAGFOS supported copper hydride catalyst. So this catalyst is extremely reactive towards this unactivated alkenes such as trans-2-butene. So the activation energy is actually about 3 kcal lower than the SAGFOS supported copper hydride catalyst. So this type of reaction actually set a good question for us, like what's the origin of the reactivity of this DTBM SAGFOS supported catalyst? And then our approach, as I mentioned, is we use those energy decomposition to separate the computed activation energy first into 3 different terms: distortion, through bond interaction, and the through space interaction. And we did this with a number of different internal and terminal olefins with both the DTBM SAGFOS and SAGFOS supported copper hydride catalyst. First, we found this very interesting correlation between the activation energy and only the through space interaction term. So what this correlation tells us is, it is the through space interaction between the ligand and the olefin substrate that really contribute to the activation energy for most of the reactions. Use that insight that we can do the EDA calculation to separate the through space interaction between the ligand and the olefin. As you can see here, between the 2 transition states with the SAGFOS and the more reactive DTBM SAGFOS catalyst. So the only difference between these 2 interactions with the substrate is the dispersion. So there is a much stable dispersion interactions with the DTBM SAGFOS catalyst. So this is helpful for us because then we can really direct those insights into a more detailed analysis to look at the region of those ligand substrate dispersion that promotes the stability of the catalyst. We were able to identify the fact that it is the meta-terbutyl substitution on this DTBM SAGFOS catalyst that essentially stabilizes the transition state structure. And then we, as I said, the next step is to perform some experimental validation. So in this case, we ask our collaborator to measure the experimental rate constant using a number of different catalysts to use with or without this meta-terbutyl substitution. So as you can see from both experiment and theory, ligands with those meta-terbutyl substitution appears to be much more effective than those with methyl or unsubstituted benzene rings. So with those mechanistic understanding at hand, we feel like we have identified one important factor that can potentially promote the reactivity. And then we thought, can we use those mechanistic understanding as a starting point and really use a combination of a computation and experiment and use this mechanistically guided approach to design a new catalytic reaction. So again, before we started, the best catalyst was that reported in the experimental literature was this DTBM SAGFOS supported copper hydride. And from our calculation, we know the reason this is faster is because of the more favorable dispersion due to this meta-terbutyl groups. And intuitively, first look at catalyst that replace this terbutyl with a TMS. And unfortunately, we found the increase of the reaction rate is really moderate. It appears that the dispersion forces was between TMS and with terbutyl, so they are relatively comparable. So on the other hand, we were able to identify that if you replace the terbutyl with a trifluoromethyl, the reactivity also increases quite a bit. And by using EDA, we were able to identify a different component, which is the ligand substrate electrostatic interaction that stabilizes the transition state. So that can be considered between the weak hydrogen bond interactions of the fluorinated ligand and the CH bond at the substrate. So as you can see, that actually dramatically stabilizes the transition state structure. But on the other hand, the dispersion force is relatively weak. And after those, we proposed a next round of a ligand where we replaced the trifluoromethyl with a sterically more hindered perfluoroisopropyl substituted ligands. So in this case, we really strike a balance between the favorable electrostatic forces and the dispersion interaction, where the transition state is dramatically stabilized by both of those non-covalent interactions. So using this approach, and finally we did a modification of the catalyst to increase the stability, but we were able to find a catalyst that was about a 60-fold faster compared to the previously best catalyst, which is the DTBM SAGFOS. So with those promising reports, and we thought we can potentially use the energy decomposition approach in several different areas, not really just predicting catalyst with increased reactivity, but maybe we can also explain the origin of a selectivity and other chemical phenomena. So but the key is really to first separate the activation energies into through space interactions and the through bond interactions between the catalyst and the substrate. And then we can use EDA to give us chemical insights where our experimental colleagues can use to design their next generation catalyst. So just to very quickly give you two different examples, we recently collaborated with two different experimental groups where we showed our EDA approach can identify the ligand effects in terms of promoting this relatively unusual asymmetric carbon-carbon bond cleavage. So in this case, the most favorable transition state we found was actually promoted by a pi-pi stack interaction between the substrate and one of the arrow groups on the ligand. So on the right, we look at this very classical regional selectivity problem when the nucleophile attack a pi-alkene complex with a palladium. The challenge of understanding the regional selectivity was because there are always a combination of electrostatic interactions, optical interactions, steric and dispersion between the nucleophile and the pi-alkene complex in those transition states. And using EDA calculations, we were able to identify under what scenarios the dominant factor is contributing to the regional selectivity. And we believe those insights can be very helpful in terms of developing new catalyst-controlled regional selective alkene functionalization reactions. In a very last example, I just want to show you a case where we use those energy decomposition analysis to analyze factors that stabilizes this transition states for copper catalyzed atom transfer radical polymerization. This is a collaboration with Matiaszewski at CMU. We show that after we identify how those individual factors affect the transition state ability, and then we can identify corresponding physical organic chemistry descriptors, and then we can use the multivariate linear regression approach to establish this as linear equations to predict how the ligand or the initiator would affect the activation energy for this copper ATRP catalysis. So with that, I want to thank the funding agencies and my research group, and I will be happy to answer your questions.
Ken, you're still muted.
Jeremy, do you have a question?
I was just applauding.
You were just applauding, okay. But Ryan has a question, right?
You can come back to me. I need to think of how to say it.
Yeah, maybe I can ask quick one. Do you see, that current DFT gives you inaccurate results, or what is there any kind of agreement that if you run this specific protocol, you typically get what you expect to get, or is it?
Yeah, that's a great question. So first of all, I have to say, when we first work on this type of systems, right, we sort of work on relatively simple systems, because we know with transition metals there are a number of challenges in terms of the spin states and also the solvation model, etc. Right. So in this case, we sort of carefully choose a system where we think the calculated energies are relatively reasonable, because I think the catalyst and also the transition state is closed shell. The mechanism is fairly clear. We don't expect the solvent would have a at least explicit solvent interactions would not have a very big impact on the reactivities. And also, we sort of have even with that, because we're really talking about very small energy differences. We're talking about catalyst A is better than catalyst B because the barrier is lower by 1 kcal, right? So with that, we sort of have to really rely on in many cases, the experimental validation. So that's why I think this computation experiment synergy through collaboration can be very critical for this type of approach. And of course, I think our next step is hopefully we can move beyond this relatively mechanistically straightforward systems, right? We'll see, if the EDA can deal with open shell systems or cases where explicit solvent interactions may be important. Maybe we have to incorporate those in our model as well. We'll see how those would perform.
Okay. Let's see. So Ryan,
Right.
you have a question?
So the through bond and through space effects I've come across in terms of NMR measurements. So could you actually use this energy decomposition analysis to sort of build a approximate or predicted NMR spectra?
That's a good thought. As Ryan, as you know, there are already computational methods to predict NMR spectra, right? But that's I think they're quite different from what our model can describe here.
Yeah.
Especially I think if you want to do, let's say if you want to do an MR, I don't see the reason why you want to separate the through space and the through bond interactions. I just see this is probably it seems to me at least it makes more sense to really look at this within catalysis.
Well, okay, that makes sense.
Okay. Any other questions? Let me see. Okay, if there are no questions, let's thank all three of the speakers for excellent and very educational talks.
Thank you all.
You want to say anything, Jenny or Jeremy?
No, this is really like a wonderful continuation of this tradition, and really happy that we're able to, to make something of what should have been an in-person event. And yeah, thanks to all the audience, of course, to Heather as well for leading today. It was really exciting work.
Okay, fantastic.
Bye.